Ingram. I am a graduate student in electrical engineering at the University of Idaho. I'm currently taking this course through the Engineering Outreach Program and working full-time as a test engineer at Fluke Biomedical. They make test and measurement equipment for hospital technicians, along with radiation detectors for field use. Anyways, today I'm going to talk about my research involving wide dynamic range imaging. Topics I'm going to cover are, in general, what is dynamic range? What is wide dynamic range imaging? I'm going to talk about different applications for wide dynamic range imaging, particularly surveillance cameras, different automotive applications, medical imaging, and consumer electronics. Along with each application, I will show picture examples between standard dynamic range and wide dynamic range. I'm also going to discuss the different wide dynamic range pixel technologies and imaging techniques. They consist of logarithmic response, full well capacity adjustment, and dual and multi-sampling techniques. Also, I'm going to talk about Dr. I's hybrid photodiode photogate technique. To finish up the presentation, I will discuss directions for the future in addition to my conclusion. Keep in mind I will answer any questions you may have through my email, which my address is found on the previous slide. So what exactly is dynamic range? Dynamic range is known as 20 times the log of the ratio between the maximum output signal divided by the minimum noise floor signal level. As you can see in the figure, the charge versus illumination response curve is plotted. The gray area along the bottom is the noise floor region, whereas the gray area along the top is the saturation region. Signal lower than noise is considered to be in the noise floor region, whereas signal higher than saturation is considered to be in the saturation region. The area between the saturation region and the noise floor region is considered to be the dynamic range region. This is the area where the signal is clean. In our case of image sensors, it is where the signal is in the visible range. It's not dark in the noise floor region, and it's not bright white as in the saturation region. So typical dynamic range for a camera is between 65 and 75 decibels, where the typical human visual dynamic range is around 120 decibels. So as you can see, there's a significant gap between the dynamic range on a camera versus what we are able to view and see as a human. So how do we solve that? It'd be nice to be able to produce images just as we see them with our own eyes, right? So in the further slides, I'll discuss different methods and techniques for being able to solve this problem. So what is wide dynamic range imaging? Wide dynamic range imaging is an imaging application which captures across a broader range of light wavelength or frequency. By capturing a broader range of light, it allows for imaging in dark or noisy environments and also in very bright or saturated environments. I took these two pictures above, the one on the left using regular imaging and the one on the right using the wide dynamic range feature on my camera. As you can see, the up-close trees are much more visible in the right picture compared to the left. In the left picture, the dark trees can be considered in the noise region, whereas in the wide dynamic range picture on the right, the trees are no longer in the noise region. Also, if you look at the skyline, the picture on the left is very bright and in the saturation region, whereas the picture on the right using wide dynamic range isn't saturated as much. Also, one drawback of wide dynamic range is capturing scenes with high-speed moving objects. Such as the van, you can see the blurring elongation effect towards the back of it. And the semi-truck, the front of the trailer is blurred. So typically for wide dynamic range pictures, you want to capture shots with minimal amount of movement as possible. There are several applications for wide dynamic range imaging. The first application I'm going to talk about is in the medical imaging industry. For example, two uses of image sensors are used for the laryngoscope, which is used to obtain a view of vocal folds and the glottis. Another example in the medical industry is the bronchoscope, where a doctor views the inside of the airways for examining abnormalities such as foreign bodies, bleeding, tumors, and inflammation. The picture above shows a small image sensor similar in size to the lead of a pencil. Examples in the automotive industry are lane change sensing cameras. Notice in the far left picture you cannot see the potential bypassing car, which may result in an accident. In the right picture, the SUV could back into the person walking past the garage door entrance. In both cases, also there is shown a wide dynamic range picture where you could see the bypassing car clearly and the person walking past the garage entrance clearly. Wide dynamic range imaging is probably the most important when it comes to security surveillance systems. Notice the difference between the two pictures. The picture with the conventional camera is pretty much considered useless compared to the wide dynamic range picture on the right. You can clearly see details of the person, the male behind the woman, compared to the left picture you can't see hardly anything. Some other applications consist of high-definition video recordings, such as movies or the example pictures seen here. In these pictures, at the top of the page, they are using a single frame dual exposure. Notice how there's a long exposure, more saturated image, and a short exposure, less saturated image. Both of these images are combined in order to create one single dual exposure image, which shows common details amongst both images. You can clearly see the clouds in the sky, a large tree, and other details on the buildings in the dual exposure image. Wide dynamic range imaging is also very popular in consumer products. In most of the current smartphones these days, there is a high dynamic range, or HDR option available to capture images. I capture the picture on the bottom of the page with my GoPro in wide dynamic range mode. Notice how there are very few shadowed, noisy areas. Also, because of the subject not moving, there are no blurring effects. Other applications of wide dynamic range imaging can pretty much be anywhere you can think of. Essentially, anywhere we need to view information that may otherwise be in a saturated or a noisy state. Now I'm going to talk about wide dynamic range pixel technologies and imaging techniques. The question remains, how do we increase the dynamic range? Well, based on the signal-to-noise ratio formula, there are two options. We can enhance the signal or suppress the noise. From basic observation, if the signal level increases, the signal-to-noise ratio increases. And if the noise level decreases, the signal-to-noise ratio increases. We can obtain a nonlinear response by using unique pixel architectures of a photodiode and a diode-connected MOS transistor. The output voltage of the photodiode is logarithmically dependent on the light intensity due to the subthreshold operation of the diode-connected MOS transistor. Problems with logarithmic response leads to low contrast and loss of details. Mismatch between transistors will create nonlinear fixed pattern noise at the output. Responsive readout is light dependent, meaning low light equals slow readout time dependent upon photodiode capacitance. The problem is nonlinear output makes color signal processing difficult. Because the contrast ratio is sacrificed and fixed pattern noise is increased, therefore dynamic range is low. And typically, in addition, there is large temporal noise. In the circuit, Q2 and Q3 act as amplifiers, whereas Q figure, the response curve has a larger dynamic range due to its inherent nonlinear response. Another method to increase the dynamic range is to increase the well capacity. As you can see in the figure, by changing the reset signal multiple times or controlling the V-reset pulse voltage on the photo gate, you can change the well capacity. This provides for a nonlinear response. In the case of well capacity and adjusting, increasing the dynamic range directly lowers the signal-to-noise ratio. It is easy to implement pulsing the reset signal. However, adjusting the well capacity causes more noise, including fixed pattern noise. This increase in noise decreases the signal-to-noise ratio. I mentioned the inverse of this phenomenon in a previous slide. Two more methods for increasing the dynamic range is the dual sampling method and also the multi-sampling technique. Dual capture implementation is not too difficult, and there is plenty of time between the two captures to read out the first capture. A high signal-to-noise ratio is achieved in regions of moderate light. However, a wide dynamic range image may look segmented. Multi-sampling technique using in-pixel analog to digital conversion relies on capturing several images within a normal exposure time. Short integration time images capture high light regions, whereas long integration image captures low light regions. Multiple sampling achieves higher signal-to-noise ratio than well capacity adjusting for the same increase in dynamic range. As seen in the pictures, 6 images were taken at different integration times, and then details from each image were stitched together in one final wide dynamic range image. The problem with multi-sampling is this technique is difficult because it requires very high-speed, non-destructive readout. Also, it requires on-chip memory and other electronics in order to reconstruct the several images into one high dynamic range image. Even though I just talked about some disadvantages of the multi-sampling technique due to high cost, one of the major advantages of this technique does allow for image sensor response using a continuous adjustment technique. This becomes very useful depending on the amount of light present in the subject you're wanting to capture. By having a dynamic or a changing image response, we can capture light levels on both ends of the spectrum without too much noise or too much saturation present. I'm now going to talk about other hybrid techniques for wide dynamic range. In particular, I'm going to talk about University of Idaho Associate Professor Dr. I's research of the hybrid photodiode photogate imaging technique. From now on, I will call it the HPD-PG technique. Increased dynamic range is possible by using a standard 3T CMOS APS pixel with a larger pixel capacitance after a known set threshold voltage level. Also, the HPD-PG technique changes the light response characteristics and the sensitivity. Notice in the picture of the cross-section of the HPD-PG, the same control and readout electronics as the 3T CMOS APX pixel are present. In the HPD-PG pixel, a NMOS capacitor is surrounded by the photodiode diffusion area on both sides. Also, the reset signal source diffusion is the same as the photodiode diffusion area. The gate of the NMOS capacitor is connected to a DC bias level. By setting the DC bias level below the photodiode reset level, you get two capacitances, C1 and C2. C1 is related to the photodiode, whereas C2 correlates to the NMOS capacitor. If the photodiode voltage, VPD, falls below the bias level, C2 becomes present and the NMOS capacitor operates in the saturation region. Operating modes. If the DC initially high, and pixel capacitance C1 is low up until the first knee. Beyond the first knee, the NMOS cap capacitance is added, which in turn decreases the sensitivity. Upon the signal saturating, the second knee appears. In order to increase the exposure, the DC bias level is increased, or the gate area of the NMOS capacitor is increased. This provides for a wider dynamic range. By continuing to increase the DC bias level, the larger pixel response range you get. Dr. I was able to use a 5-volt DC bias level, which resulted in an increase of 10x full well capacity improvement, and light response range increased approximately 5 times. This is a significant increase in the dynamic range. There is a large market for having increased wide dynamic range image sensors. Our eyes are able to achieve wide dynamic ranges, so there should be image sensors that can reproduce what we're able to see as humans. I feel that wide dynamic range image sensors are very important, especially in surveillance camera systems. There is no point having a security camera if you don't have a high quality camera. By high quality, I mean a camera that can capture images with wide dynamic range in order to capture as many details as possible. Also, I feel there are several other medical imaging applications where we can use wide dynamic range imaging. Imagine all the possibilities to be able to see inside of a human body for diagnosing different types of illnesses and accidents we may have and we need to determine a solution for. Our cars we drive are going to keep evolving, and by having wide dynamic range imaging systems, we can have technologies such as adaptive cruise control, drowsiness detection, blind spot detection, parking assist, potential night vision, and lane departure warning. Another application I have seen is carpool lane cameras, which require wide dynamic range for capturing images at night. In addition, we as humans are always going to want the latest and greatest camera in our pocket built right into our smartphone. All of these applications beg for continued research in wide dynamic range imaging. In this presentation, dynamic range was introduced, which is the ratio of maximum output to minimum noise floor signal level. Also, the concept of wide dynamic range was introduced and the need for it. Wide dynamic range image sensor applications were discussed, including medical imaging and automotive industry, security cameras, high definition video recording, consumer products, etc. Wide dynamic range technologies and techniques discussed included nonlinear logarithmic response, well capacity adjusting, dual sampling methods, multi-sampling method, and the hybrid photodiode photogate method. Also, directions for the future were provided. Thank you for the opportunity to present on wide dynamic range imaging. I invite you to send any questions you may have to my email,